but I'm talking about these very early systems that both prove theorems automatically given the theorems and try to discover conjectures and prove them. So David McAllister is an early AI pioneer still active who wrote his thesis about this. And this is one of the early works that based it much more on rigorous mathematical foundations and set theory as opposed to something, collecting logic and heuristics. And I'll come back to some of his ideas later in the talk. Okay, so now just to put it in a nutshell, we want to find an algorithm to generate provable, interesting statements. Okay, and provable, we know what that means. Interesting, well, we don't know what that means, and humans ultimately judge. But there have to be some criteria that we can program that correspond in some way, that sift out this, huge exponential set of true facts or provable facts, and select the ones that we think have some agreement with what we think are mathematics. And then I'll actually add criteria to that later. But another point to make obvious at this point is that when you say generate, of course, you don't start from zero. You start from something, and you could start from just logic and set theory. That would be in some sense, ab initio. The math zero program was that. And then, of course, start with, say, all of current mathematical knowledge and try to now generate new facts based on that. And they're obviously both interesting, and we should distinguish them. Okay, so I'll try to later in the talk make precise versions of these. Again, on the face of them, not surprising in themselves, but at least concrete reasons to believe that something is interesting, starting with it being new. If it's proved, then very good. But if it's a conjecture, it should not be easy to find some falsification of it. It should be useful for the many things that we do with mathematics: solve problems, find proofs of other statements, communicate. In some sense, it should be surprising. That one might sound even less objective than the others, but we will have to talk about that. Okay, so what's the previous work in this field? And to my knowledge, there has not been much recent work on this, in part because there are so many other incredibly interesting things going on. But there was quite a bit of work again in the 80s, the 90s, the 2000s that was in this symbolic or good old-fashioned AI framework. And there's a very nice survey paper, Colton, Bundy, and Walsh, which I recommend. And this part of the talk is largely drawing on that. So they looked at 5 of these math discovery systems in some detail. And just to give a sense of what they could do, they each have a specific domain, such as a graph theory, the system GT, Susan Epstein, which discovered, in the sense that we'll describe, concepts such as a connected graph, a acyclic graph, a tree graph. It's conjectured and proved that if it's connected and acyclic, then it's a tree. So that's something. The HR system of the authors of the review discovered various group theory concepts on this level. The graffiti system also covered graph theory, but looked for inequalities between basically invariance of graphs. And these apparently were interesting enough to lead to over 60 published papers proving or disproving these conjectured inequalities. Okay, so what are they discovering? Well, in some sense, they're discovering concepts. Well, what's a concept? Well, a concept is a very rich thing, but each of these programs made it a much simpler, concrete thing in various ways. But what they all pretty much did was say that there's some set of objects within the big class of groups, say, and made some formal specification of a subset of these objects. So this wasn't a universal thing, but the cases like GT and HR that I talked about work this way. Math zero works this way, and the goal here is really to describe very general objects as signature axiom classes in the sense of Bourbaki. And then conjectures relate concepts, for example, that as we described before, connected plot, and acyclic implies a tree, or in that case is equivalent. And they would make conjectures either, ideally against logical statements, in most cases as concepts in this sense, these formal specifications that I'll get into. And then they would produce lots of examples, instances, graphs in the case of graph theory, and then be able to do inductive reasoning, check that some claim is true on a bunch of examples and then conjecture the general result. Okay, so again, ideally you would have very general mathematical higher order logic available to define your objects of interest and instances are satisfying some set of axioms. Here's some lean code for a few of the semi-group axioms. And this is certainly at the time and still really too hard to get very far. You know, both because, again, automatic improving is made a lot of advances, but it's not anywhere near human level. And then very often, given the original axioms, the instances, it's very hard to construct instances. If you think about groups, well, the groups I put on the slide here are pretty simple, but groups rapidly become very complicated in terms of these fundamental axioms. And then if you look at an actual book on group theory, they will talk about the groups in many, many other ways. So if you start with a signature axiom class, you're deep into that level of difficulty already. Okay, so on the other extreme, you could say, let's just take a very set of objects with a very concrete definition. We could look at plane geometry and just say, well, I'm going to consider a set of points with some sort of constraints, such as I draw lines between pair of points. They are parallel or they are not parallel. And then we have specified, certain constituents exist and they satisfy relations. And that's it. That defines a class of geometric figures, a quote concept. And you could ask, does it have instances or does it not? Is this an inconsistent set? And then this is close enough to, you can basically, solve to a large extent solve using, linear algebra inequality solvers and so forth. So this is on the border of what we might call math discovery at this point. Okay, this is the GT system. So the idea here was to describe a set of graphs by constructors and constraints. So there's a set of operators that can be applied in some sequence. You can choose from the list probabilistically, and then you create points and edges using the operators and satisfying certain constraints. So if you look through here, you have operators that AX creates to point X, AYZ creates to edge Y to Z. You can explicitly enforce in terms of these simple set relations that graph say doesn't have a cycle, and so this was the concept. Move through this space of definitions of subsets of graphs. And how does it move through it? Well, all these systems have what you could call an exploration loop, where there are various operations that it can try to do. It can try to generate a new concept. It generally did these things in not a totally random way, but not a very sophisticated way. You might mutate, change some term in the definition. You might say take and or merge two definitions. Simple rules of formation that don't have to be logically sound rules of deduction, because then the goal is going to be to generate instances and use the structure of the instances and inductive reasoning to make these conjectures. And so GT here, for example, is very explicit. This is basically telling you how to make an instance, whereas, for example, signature axiom class in general is very difficult to even know whether there are any instances. Okay, so that was the kind of style of these systems, and then they faced this problem of what generates all these conjectures, and some of them, it falsifies some, but what are the interesting ones? And that was the focus of this early review. So they did go through, this is, where I took that list of interestingness criteria, and the paper explains in some detail how these things are explicitly encoded in the search procedures and these exploration loops. And, some are pretty obvious. If you have a list of all conjectures you've considered, you can tell whether you've made a new conjecture. Some are heuristics that are of great generality to consider, for example, more general conjectures first. And a lot of it was domain specific and, kind of crafted to the thing. And ultimately, these systems, you had to craft these definitions of concepts, these formal systems, so that simple mutations would tend to produce, not always, but tend to produce interesting things from the start. So it was like a lot of the GoFi. It shows that things are possible. Computers can, in some sense, create and discover, but putting in almost as much or more human effort than the results that were obtained. Okay, but still, we learned something about interestingness. Okay, so now we're fast forward, and I won't have to tell this audience about all the progress in AI and applying it to math, and then it would take more than one talk to do it justice. There's a large number of topics that we could at least survey, and I'm again, I'm here today and tomorrow, and we can discuss any of these things, but I'll try to keep the focus on the style of automated math discovery that I just reviewed, and can we do a better job with what we know now? Would doing it teach us something either about math or AI or both? Okay, so there was some sense in which those systems were discovering mathematical concepts, but we should be very critical about that point, because computers can calculate many incredibly useful and interesting and great things, but usually we don't say my computer discovered this solution of an equation, a climate simulation, or even a solution of mathematical significance. It's the people that use the computer who made the discovery. Okay, so why do we say that? Okay, well, this is a point where we really should be thinking very carefully, because again, if the computer discovers something absolutely new, then it matters less how it happened. We can judge it, but if the goal is to learn something about exploration and discovery, then this is important. What is a discovery? And I think we should take the stronger position that even computing and showing that some mathematical object exists doesn't by itself count as discovery, even if it was never done before. And we should put some criterion that the agent making the discovery should have some understanding of why it's a discovery and why there's actually something significant about this. I mean, again, if there's some set of axioms and there's only one instance and you didn't know that, then you might say, well, that's a discovery, but you should have known those facts to justify the claim that it's a discovery. And more typically, there are many objects, the many graphs of these conjectures we talked about before. And why are we focusing on this one, or why are we focusing on this particular conjecture about objects as opposed to all the others? And so that's, of course, where the interestingness gets into the game. And there was a sense of interestingness programmed into these systems, but the question of understanding, I think, deserves some answer. Okay, so there was a measure of interestingness. It was sort of, to a large extent, implicitly encoded in the search procedures and heuristics, but it's very hard to argue that the system's understood in any way that this was interestingness. Why do we care about this, and so forth. And of course, so then the reply might be, but this is really much too high a bar, to actually understand things. Well, humans understand things. We really need a computer to understand things in the generality to claim to have solved this problem. We better not require that, or else we would turn the problem into AGI. But I think we need more, or at least it's very interesting to ask, what is more of a criterion of saying the system, the agents, understood something about why that was a discovery? Okay, so one way you could ground it, of course, is to say, ultimately we have this problem. Let's take number theory. Fermat's last theorem motivated a huge amount of effort in number theory, and lots of things were considered interesting because they might solve that problem or seem like progress towards that. I mean, that's historically, certainly for humans, was a very, I think, clear historical source of interestingness. And you could certainly program that. You could say, my system, I'll put a big term in the objective function for solving Fermat's last, proving Fermat's last theorem, right? I mean, or just, but, again, that's far beyond what any system could actually use at this point. And then, of course, this notion got generalized in the history of mathematics. Let's pose very broad questions like that. What big class, here's a method that solves a big class of equations. Here's this other big class of equations that we prove has no solutions. Here's this third class that we prove it's hard in some sense to find out whether there are solutions. And then this could be programmed too. This will be, again, a class of problems which will be the source of interest ultimately. And when we use those terms, useful, that this is going to be very helpful in terms of, giving meaning to these terms, useful. So I'll come back to that. And so I think utility is a strong thing to ground it on, because if the system can solve the problems, well, it's true, it may not understand why all the things that it discovered along the way. It may not be able to explain them. It may not have a deep understanding, but at least has the understanding that it used them to solve the problem. It's again something that you could work with and claim that's a form of usefulness, of understanding. The utility, the interestingness. Okay, so of course there are other, and I'll say a bit about these other possible bases for interestingness that you could draw on human experience, and I'll come back to this a bit. Okay, so I'm going to put in a brief interlude because I put this list of very interesting AI topics, but one that I'll argue is quite relevant for us is inductive program synthesis. Okay, and so what's that? That's a classic problem on which there's been a lot of very interesting recent progress. So in the usual form, you give a few input-output pairs. So in this case, sequences, finite, lists of integers. 1, 2, 3 is the input. 2, 4, 6 is the output. 4, 3, 4 is the input. 8, 6, 8 is the output. And then in modern terms, you might say, okay, I'm going to make a feed-forward network or something that learns that relation. But the problem here is not that. The problem here is to somehow find or learn a procedure that produces a program, an algorithm that agrees with the examples you're given, but also is in some sense simple. There's some sort of inductive bias there. And so that's, it's not math discovery in itself, but as it is plausible. And I'll argue that it's in the ballpark. It's pretty closely related to math discovery. And there are variations on this. For example, we could just take the list of outputs. Like we could take the online encyclopedia of integer sequences. Can the system come up with programs that generate those sequences? And there are interesting works about that problem. This is a slide I wish, again, you could probably, in fact, there are whole talks on this. Is the dream coder system of Ellis et al. And I won't have the, again, time, but towards the end, I wish I did. So what are the ingredients of this? Well, there's some neurally guided search that again does that simple thing, takes the input-output pairs and tries to put out a program. But then the novel thing about this system is that once it solves some subset of the problems, it looks through all of these programs that are generated in metadata, and it can identify common small units, say subroutines within those programs. It can refactor, that's that bottom left box there, and say, here, this has appeared in many of my the solutions I found so far. That might be a useful subroutine to define and put into the library, so that automatically goes back and does that. And so that's a very concrete form of abstraction, and that will be one of the, not the only, but one of the points of contact with the present discussion. Okay, so we'll come back now to interestingness, having raised all these philosophical questions. Let's come back to the measures that were stated and incorporated in those earlier systems, and try to go a little farther in the more modern language. And the more modern language will probably be a language of objective functions. So we're going to take whatever, the conjecture, the object, whatever it is, and we're going to try to find some concrete function of it. It says, how interesting is it? And so, I've listed, again, roughly the same criteria I had before. You might also now at this point put in alignment. It might be that it's interesting in some abstract way for a system that, who knows what, solves this class of problem, but we would like it to focus more on this particular class of problems because that's what we're interested in. That would be an alignment term. And so as one thinks systematically about these things, of course, you can translate them into by now standard ideas of machine learning, that some of them you can imagine a concrete definition, but some of them you have to know things that you don't know, you don't really know to properly compute. And so you have to estimate them. And and then we'll talk about this. And then There's already a pretty long list, and it seems already kind of complicated. And so they might ask, well, could the system somehow learn these criteria? Okay, so some things are straightforward, plausibility. If plausible is not falsified either by, a conjecture is not falsified by some instant, it's not falsified by logical deduction, well, then it's plausible. That's we're granting that the system can do those things. Applicability you can quantify if you have a big database of problems, objects, statements, and so forth. You can count how many times you use something. Always in these considerations, the computer has a given time limit. These tend to be algorithms that don't have clear time bounds and then terminating algorithms. So one has to keep in mind that these things can change with time. Novelty generalizes to the idea of distances between statements. That's a very common idea in modern AI. Of course, in mathematics, there's the very central thing, which I've suppressed a bit, and it's very central in David McAllister's discussions of this topic of isomorphism. So I was kind of implicitly saying graph, but really what are we interested in is isomorphism classes of graphs, and that was kind of, again, just built into those previous systems, but has to be really considered from the start as very central. Please.
What was KB?
KB is a knowledge base, so it's just saying the state of the thing with its conjectures, its instances, its concepts, and so forth. Yeah, and so in principle, the measure of interestingness could depend on all of that. It could just be to say, your KB has this level of interestingness, or you could say, now that you've added this conjecture, maybe it's so much more interesting. So that's how you would formalize these things. I'm not going to formalize it at that level, but what should make the definitions that way? Okay, so then there's a utility and effectiveness, and there is kind of a standard definition, which is actually there in the Dream Coder as well as many other works, which is that you use things that are related to Kolmogorov complexity. You say that something has a description length, and now its usefulness, say, for making other definitions of proofs is measured by how much it shortens the expected value for which it shortens other proofs minus its own length, where you could say the same things for time. It makes it faster to find those proofs, but it took time to establish and so forth. And then this is a very general kind of thing, but in practice depends on some probability measure over the statements. And then the other issue with it is that very often what you're interested in is how good is this assumption? Do I want to put this new thing I proved in my library? Well, I want to do it if it's good for proving new things, right? But I don't know any of the new things, so what do I do? And this is, well, I mean, again, this is a problem of prediction. What are the things that's likely to be useful for proving? Well, that's something you could try to estimate using beliefs or statements about the distribution of statements. So in the end, you're going to have some sort of an estimator. There might be all sorts of ideas you throw in, some of them mathematical, some of them statistical, but this is kind of where a lot of, I think, the human intuition about these things that says that, we find something, this contribution to interesting, maybe in part is because it would be useful to go back and rewrite all your proofs, all your textbooks using this new definition. But what we tend to be also at least more interested in is if I know this, I can then go on and do my future research better. And that's some sort of estimate, and that's the estimate that is being talked about here. So it is, I think, a thing that people do in their reasoning, and it's sort of explicit in this discussion. And then plausibility has the same relation to surprisingness. Plausibility, you check on concrete examples or logical deductions and so forth, but then you're really interested in all the examples that you don't know, and now you have some fast estimator for that, which is the surprisingness. Okay, so those were some of our, how you would make some of these measures more generally defined. Okay, well, now we get to communication, and now we have to start talking about multiple agents. Okay, so this is obviously a whole nother level, but again, people do have multiple agents, and then it makes sense for them to communicate with each other. And once you start talking about multiple, multi-agents, then of course you're inevitably going to start talking about games. We don't just have one objective function. We have shared objective functions. And of course, the place where I and many people started in this modern discussion to say, AlphaGo, cool, amazing, clearly a new era in AI. Now, if we could just have the computer discover math playing a game like Go, then we would be all set. We would just train it like AlphaGo. And many people have had the idea, and it still hasn't happened. But it's not that it's a bad idea. It's just that it's not totally obvious how to turn math into a game. And anyways, it is a good idea. We can think of these actions as moves in a math game. The single agent thing is a solitaire game. There could be a multi-agent game too. And so then this kind of metaphor does help with various things. So this question about once we get into generating problems, if it's true that solving problems is a way to produce activity that leads to discovering conjectures and proving the theorems and the rest, then we need to pose problems of the right level. They shouldn't be too easy and too hard. Ideally, they'll be interesting in the end. Okay, so what's the basic move in a multi-agent math game? Well, it would seem that you have agents A and B, and agent A states a conjecture for B to try to settle. Okay, and so that's a sensible thing. There's clearly some idea of utility on both sides. A is trying to state something that B presumably can't solve. Well, that's no good, because then A can just produce this incredibly difficult problem that nobody can solve. And then there's this game called Dixit that some of you may know, which kind of gives a nice protocol for solving this problem. It probably does already exist under some more formal computer science terminology, but you have at least 3 agents. And so agent A, you could rotate, but let's start with agent A, gives the same conjecture to agents B and C. And A only gets points if one of the agents can settle the conjecture. And so if neither one, then it's too hard. And if both can, then it's too easy. So that's a nice way around finding problems with the right level of difficulty. But then it has a problem. I'll ask if anybody. Okay, so I predict that if we do this, what's going to happen is that it'll degenerate in producing lots of very tricky puzzles that really run up against the time limit. So that B just happened to make the right guess and solved it in time. And C was less lucky and didn't solve it in time. And that's why in practice, you're going to get conjectures that one agent can solve and not the other. So I think this is a step forward, but I suspect won't quite work. And then I think again but these are games that these various aspects of the objective function, the interestingness, emerge, right? So we've gotten this idea that the problem should be of a level comparable to the level of the agent to emerge from this game. And so one could keep developing this idea. And I think a way to solve this problem of the tricky puzzles is that, of course, we want results that don't just apply to solving particular tricky puzzles, but that have this kind of generality that we look for as mathematicians or mathematical scientists. And then, of course, you can try to model human societies to create knowledge, and how do they deal with this problem? Well, you get a bonus for publishing some result of great generality, and it's proven by getting lots of citations. So all those things could be incorporated into the multi-agent game, and then these properties of interestingness would emerge conjecturally from that. Okay, so let me finally talk about this idea of interestingness derived from solving, interesting classes of problems, or thinking about interesting classes of problems. And this part is new. So I hope it will stimulate discussion. There'll be many gaps in it. And just again, for definiteness, let's talk about the system that's exploring graph theory, and it can produce graphs. It can produce these sets of graphs, what were called concepts in this language of the GT system. There can be statements about graphs that are precise logical statements, and if we conjecture one, it can try to prove it from other statements. But where did the conjectures come from? Okay, so now the idea we'll pursue is that we have given it this class of problems to solve, and that's its goal. And it's true that this is, often, in modern systems, one has a list of problems as the training data, dream code or deep code or so forth like this. But now we're going to give a very broad class of problems where maybe it's useful to give some particular ones, but we can also just sample from a big distribution over problems. So we could postulate a probability distribution over graphs, and then there's the graph isomorphism problem. You can't get much more basic than that. You sample two graphs from the distribution, and are they isomorphic? And of course, there are some representations where that would be instantly obvious, but if it's the standard kind of vertex edge representation, it's not, because there could be a permutation of the vertices that make them isomorphic. And in general, this is known to be a very hard, not NP hard, but hard problem. But usually it's quite easy. Two graphs to have different numbers of vertices under the strict definition are not isomorphic. And then there are many invariants of that sort that can solve lots and lots of graph isomorphism problems. So this might be a good laboratory to start with. Can the system discover the invariants or other concepts that allow solving lots of cases of the graph isomorphism problem? Okay, well, so how does it try to solve a problem? Well, we can give this a name. We can call it a problem-solving strategy. Okay, and what is a problem-solving strategy? Well, it might be many things, but suppose, well, we give it, in this particular case, two graphs. It has to decide whether they're isomorphic or not. And we're going to make a program. The system has learned some sort of a program to solve the graph isomorphism problem. And how could you get that? Well, you could have a learning algorithm that produces a program that solves these problems. And then it could be using definitions of invariance. Again, ultimately, this exploration loop is going to include the kind of ingredients that we talked about in the early systems. It will, just to some extent, it will make random definitions and try them out. Of course, that's a very, costly, very inefficient way of discovering things, but sometimes discoveries are made that way. But, much more often you pull out some piece of something that already worked, or you find the common ingredient in various solutions that worked, and you say that common ingredient now is going to be the basis of a definition of a function or a relation or whatever. And this ways of phrasing the problem starts to sound a great deal like the deep coder, the dream coder, the inductive program synthesis, to say that we're really programming a system that learns how to solve these problems. The differences are that we first of all take mathematically richer problems. I mean, integer sequences, of course, are very rich, but it's hard to discover the rich things about them without knowing quite a bit about algebra and math. And other domains are probably simpler things to start with. On the other hand, of course, an integer sequence can be specified in just a few tokens, and a graph tends to be a much more complicated object. So I don't think you would just plug this problem, as I stated it, into some modification of dreamcoder, but I think it's very much in the same ballpark. Okay, so the isomorphism problem is already very rich, and then a few more problems like this, the subgraph problem in the case of the graph theory and so forth. We've clearly put something in, but to the extent that they're very general classes of problems that make sense in great generality, you could argue we're only putting in, what is it to think like a mathematician? That seems fair. Okay, and then of course another problem that very much motivated by the inductive program synthesis, to say, given a graph, given an object, rather than list all the vertices and edges, is there some simpler description? Is there some program that generates the graph? And so inductive program synthesis, is that problem? So again, making that relation. Okay. So again, you have lots of details. What are the probability distributions that you take? Should the system be able to pose them? Should you give it an initial set? Let's take the graph thing. You might say, well, I mean, there's obviously very simple ensembles of random graphs, but you might also say, I'm going to put in the Cayley graph of the S5 or something, and see if it can discover something about that. And then, well, it's true, we put something in. This is some particularly interesting thing. This is in some way an analog of saying we have this natural world out there. There are all these amazing regularities of the natural world, which have inspired so much mathematics. Well, a simpler version of that is to say, here's this amazingly regular graph. See what you can discover about that. And So anyways, I think that illustrates the idea. Of course, there are lots of other types of discoveries and questions you might hope that a system like this would do, which I think were not covered by the things I said, but would be, interesting to try to fit into this framework. Because this is, again, the same style of exploration loop that was used in the earlier systems. And this part is not so different from what was tried, what was used in those previous systems. There are very interesting examples of a language model works that do this sort of thing. This, for example, the work of Romero Paredes, the DeepMind work on producing cut set solutions. They use this very clever genetic algorithm where you combine two programs by feeding them into a language model. So there's all sorts of new things you can use to improve the technology. Of course, the danger of using a large language model is that it already knows all of this stuff in an uncontrolled way. So it's hard to know whether your system discovered something. But in any case, it's worth trying. Okay, so what will we learn by doing this? Okay, well, yeah, obviously very interesting to know if anything like this works. But again, I would argue that this is at least a small step towards addressing this criticism that I made earlier, in the middle of the talk, to say that there can be some criterion for interestingness, but if you just put it in, then it's ultimately the user of the program that's saying that's interesting, thanks for pointing it out to me, as opposed to the system somehow knowing that this was a discovery worth making, and now we've tied it to problem solving. So if the criterion is yes, this thing was useful for solving my problems, then that, again, is a very limited form of understanding, but at least it's something. So okay. Okay, so to conclude, well, I described the automated math discovery problem. I described these early, good old-fashioned AI systems, which I think have a lot of content. They show the problem does make sense. They just don't scale like a lot of the early AI. And then I spelled out some of these components of interestingness in more modern terms, but an objective function with 12 terms is probably not the most fundamental description, and there might be some ways of getting to emerge, and I argued that multi-agent systems, interestingness could emerge in various ways from those. And then finally, I gave this kind of sketch of a proposal for using usefulness for problem solving in a math discovery system, which is a lot like inductive program synthesis. Okay, so thanks for your attention.
Thanks. Are there any questions from the Cambridge audience?
I have more like clarification.
Yeah.
Page 22. There's a very interesting graph here. What I don't quite understand is this neural network looking stuff, right?
Okay, well, this could be a talk in itself, and I'm sure it is. It's not my work. It's the work of LSAL on the gene coder. And I can, in fact, refer you also to there's a more recent version of this called Lila, which we had a talk in my seminar. I can send you the recording to that, which would be better explanations of these things. I mean, basically, the rough summary of what's going on the top there is that, you can think of something like a feed-forward network or a transformer that has really learned to take the input, the input-output pairs, the inductive, data input as the input, and puts out a program as the output. And again, transformers we know have some ability to write programs, and it's not, again, it's established that at least for simple problems that it will have some ability to solve the problem. The new thing is not so much that. The new thing is that it then takes this big list of problems and programs that it produced, and it's able to factor out common subroutines, if you will, the ingredients of these programs, and make them available, and then reuse those and retrain the network to be able to use those. So that's kind of the point of this work.
So ultimately, the target of the function.
Yeah. So yeah, I mean, I think this guy starts off by being given some actual programs, which are solutions, and then see, the way you can train a lot is you can make a random program, or you make a well-chosen random program, and then use it to generate input-output pairs, and then invert that relation. See, so then you can get a lot of training data. Yeah.
And I guess more generally a question is that, So when we talk about all of these interestingness and relevant ideas, do we have like a performance metrics or something to evaluate these?
Well, so you're asking like some sort of a priori, because again, a good part of my talk was to, try to define a metric for interestingness. And so, but how do we know it's interestingness? And ultimately, people would look and say, yeah, it's doing a pretty good job. I mean, that's what ultimately how these earlier systems were tested. Now, you might ask, is there some sort of more a priori but less practical measure of interestingness, which we could then compare to the more practical but less well-motivated things? And I think that, indeed, that's clearly a important research topic. I mean, these multi-agent things, to my mind, were much more kind of a priori and natural than the explicit criteria.
Thanks.
Yeah.
You use the length of proof
Yeah.
to compute interestingness.
Well, you could. That's right. A proof should be simple. The one that I discussed in more explicitly was this measure of how much does it short. What's the expected amount it shortens the length of other proofs minus its length. There's no universal definition, but in any given proof system, there's a definition. It's the obvious one.
So given proof system, seems like
Oh, yeah. Excuse me. I mean, yeah.
So it's the length of proof given proof.
I mean, we're choosing a particular system. There's like, you have a resolution proof of, propositional logic and so forth. And it could be the number of steps in that, or it could be some other proof system. So there's no universal thing, but in any given system will have some proof system, and then its length in that system. Right? No, it's very hard to formulate universal measures of interestingness. It's really unclear. It's a very, very deep question whether that exists at all. But certainly for explicit practical definitions, I think this works, right? I mean, yeah. I mean, well, no. I mean, these are very hard questions in complexity theory, even to relate the lengths of proofs in different systems. I think so. It would be hard to get anything more universal.
The vague idea is specialized.
Oh yeah, well that's right. I mean, I didn't put that. Definitely, you could put that one in, but the one that I wanted to emphasize was that you look at there's always some cost to adding a proof to your library, but then how much does it save in making other proofs? You want to compare that. You want the proof. You're willing to spend some effort to make the proof as long as it saves more effort in making other proofs. That's what I was trying to formalize.
Maybe what's interesting there is not the length of the ultimate proof, but the difficulty of finding proofs.
Yeah, that's right. The time version of this is arguably more. Yeah.
We have another question over there.
Are there limitations to this approach? If you gave it a list of times tables modulo say 5, would it be able to discover the idea of groups?
Yeah, that's an excellent question. I mean, obviously, I think the thing would be to pick the simplest domain that seemed non-trivial. It's probably not groups. I mean, and historically in mathematics, it was not groups, of course. So, we're definitely at the point where getting things to work is interesting, and limitations. Well, they all have limitations. I mean, we could try to ask why. Is it essentially true that the group concept is more difficult than, say, the concept of solving equations, which was certainly the case for humans historically? Why is that?
We had another question.
Yeah, hi. I just have a slightly more tangential question.
Yeah.
There was a paper last year that was training a model to learn the interesting concepts in Minecraft game.
Right.
Letting it watch tons of Minecraft YouTube videos.
Right.
And they sort of discover like, oh, building a diamond sword is interesting. I wonder like what your thoughts are on, do you have an objection to using this approach for mathematics? Like maybe just that a model.
Well, I don't think I've studied that paper. I mean, can you say a little more about what it's doing?
Yeah, so it was feeding the model with a lot of Minecraft YouTube videos.
Right, yeah.
Sometimes the person who's narrating the video will say, oh, this is interesting.
Okay, right,
Exciting,
right.
blah, blah, and they they did it in a very unsupervised learning way,
Okay.
by matching the video with the caption. And I wonder, like, if you train a model on mathematical blocks, sometimes you would say, interesting form here. Do you think that would eventually produce a useful measure of interestingness?
It might. I mean, I'll just start with that essential distinction that there are kind of from the start, two things you can do. You can try to use as much human mathematics and literature and the rest as possible, and then let the system learn from that. Or you can totally separate yourself from that and say, I'm interested in discovery as a process, and I probably won't discover something which is new to me, but I want to understand what it means to discover. And I was kind of more focusing on that second one. Yeah.
Yeah, so you talked about this inductive program synthesis, and in the modern times it would look like, basically feeding a bunch of prompts into an LLM. But yeah.
That's not inductive program synthesis. Well, I mean, it might be like few shot learning, you could say. That's right. Yeah.
Or yeah, in the LLM, they're like,
Yeah. Okay. You could do that with the language model. Yeah.
But then I guess, how would you unify that? Like, what's a good way to unify that with what you also said about that a system should be aware of?
Yeah, okay, I mean, Lilo did it that way. Lilo used a language model, and then they had some other very clever things to do again, the novel thing is not so much that, it's to extract out the pieces, the common subparts of the thing. And they had this very sophisticated kind of graph-based thing called Stitch. But then they also had something where they said, let's take the program, let's then reverse engineer it back into some natural language description. And let's try to use that to help extract out, useful or useful pieces. So again, that system, unlike the original Dreamcoder, was very much in this. Again, there's this distinction between the system that kind of uses as much human knowledge as possible, the large language model versus the language model. The large language model is trained on everything, and it's far more powerful. But who knows whether it's discovered anything, because there's so much out there that it was told, and
it doesn't understand, I guess.
Well, we could debate, I mean, again, I can imagine GPT-7 will understand some things, but again, if it's being fed it all in its training data, did it discover it? Right? then you're kind of forced to ultimately this criterion. Gee, it's got to discover something which is new to humans also, which would be great. But if you, again, take this other posing of the problem that doesn't give it all the human information, then you can say, yes, I really discovered the concept of group or whatever for myself, and understand what that meant.
Yeah, in terms of the inductive program synthesis, I believe actually most probably in terms of iteration focus on the closed work assumption with the determinist and fixed combined binary iteration. But if we extend that a bit further for the open work assumption in terms of knowledge base or knowledge graph, we have for some unseen entities, or even for the program representation itself for some new predicate creation for
Right.
to become more view on this area of research.
Well, that's a pretty broad question, and we'd have to, I think, agree on terms. I mean, we could mean the terms closed world and open world in different ways, but I would tend to, once I hear the word open world, I would tend to already say it's not mathematics anymore, because there's not underlying precise definition of the things. Is that fair, or is that not fair?
Probably not that open, for example, in terms of the time.
Okay. Yeah. Well, you can formalize time in mathematics, but it's one of the harder things to do. I mean, certainly you can have functions of time and systems that evolve in time, and then the natural thing, I think, would be to work with the function of time, or with the sequence of states changing in time as a mathematical object. So yeah, I mean, again, I mean, it's a very rich area of research, but starts that there's this essential thing which is kind of, I won't say non-mathematical, but beyond standard mathematics, I would say. Yeah.
And I have another question in terms of the methodology to
Yeah.
how to find the search the problem. So of course, yeah, we got the pure exotic search, the symbolic way,
Right.
or the neural-based method.
Right, right, right.
Do you recognize any other possibilities?
Oh, yeah, I'm sure there's an infinite number of ways to do these things, and they're all interesting. And I'm trying to pose a problem, which if one has success at it, we learn something. You know, and any way that the computer solves the problem could be interesting from that point of view.